we are going to cover plasmonic waveguides. So it would be helpful if you read these lecture notes with the lecture notes on dielectric waveguide, okay, because they kind of go together. Okay, so let's begin with this problem. So plasmons, surface plasmons, exist at the interface between insulator and metal, right? So it's like having this electromagnetic wave form. So evanescent wave in surface perpendicular direction, but oscillating in surface parallel direction. And the dispersion relation of these plasmons will look like this. At the low energy, it approaches to the air light line. And then at high energy, it approaches to the, as the frequency approaches to the surface plasmon energy, it tends to, I mean, the wave vector tends to diverge, okay? And this is the main kind of an advantage of having plasmons. It has really high K vector. High K vector means small wavelength. So small wavelength means the plasmons are smaller than the photon, and that's kind of the most important property of plasmons. Okay, so now we're gonna discuss these two problems, okay? What happens if we make two interfaces and make these two interfaces closer and closer to each other, okay? So that the plasmons in each interface kind of feels each other, okay? So MIM case and IMI case. Okay, so you can easily imagine the situation like when the spacing between this metal dielectric interface, let's say this is A becomes very, very large, then what happens would be you ended up having two independent plasmons, right? They are not coupled with each other. So then, so if A goes very, very large, of course, the dispersion relation will be similar to the single interface case because they are not interacting with each other. But as the interaction and as the thickness becomes smaller and smaller, then these fields feel each other and the dispersion will deviate from the single interface by a lot. Okay, so that's basically a story that I want to display today. Okay, so I want to approach this problem using an analogy again with mechanics, simple mechanics. So this problem is very similar to two mechanical oscillators coupled with each other. So one oscillator, oscillator 1, the equation is F equals ma plus k1x, which is a restoring force, this k, small k1, and then kappa, which is the spring constant connecting these two, and then x1 minus x2. So x1 minus x2 basically gives you how the net displacement of this kappa thing. Okay, and similarly, this mass 2 feels the force of kx2, which is the main force, and kappa x2 minus x1. This is like a coupling force. Okay, and if you write this into a matrix form, the matrix form looks like this, and then eigensolution can be easily solved by doing diagonalization, matrix diagonalization. And you can see here the omega zero. So the solutions are two actually. One is omega zero, which is m kappa plus k plus kappa divided by m square root, and then gamma here is basically the characteristic frequency of this small coupling spring. Okay, so for high frequency mode, which is omega plus, taking the plus sign here, x1 is equal to minus x2, which means it's out of plane. So out of plane. So it like oscillates like this. x1 and x2 are oscillating in opposite direction. Okay, and then low energy mode, x1 and x2 goes together. Okay, as if there's no kappa here. So this is pretty easy thing, and probably all of you already knew this, but this gives you interesting insight about also on optical coupling or optical wave mode coupling thing. And of course, now if you go to kappa goes to zero limit, so if you make kappa becomes zero, then this is basically two isolated system. You have one resonator here, the other resonator here, and your solution should be omega zero is just the square root of kappa over k over m, right? You have just only one solution degenerated at this frequency. Okay, and as you increase kappa, and you basically have an energy splitting. One mode is out of phase, the other mode is in phase. Okay, so keep this in mind. Okay, so I looked for if there's any interesting video about this, and I found one. Let's look at this.
Now, because there are two pendulums, it turns out that all those complicated motions you saw before can be broken down into a mixture of two motions that we call modes. The first one is this one here, where the two are swinging exactly the same time in the same way. And you see that they always stay in sync. Neither of them ever stops. And the other motion, sometimes called a breathing mode, is when they're moving in opposite directions, like this. They're still in sync, but always moving in opposite directions. All of the other complicated motions that you saw is just a mixture of these two modes.
Okay, so interesting video, right? So this is basically give you a coupled oscillator system, and again, as this video said, there are two modes. One is going together type of mode, and the high energy mode is breathing mode, which is doing like this, doing opposite. Okay, so now with that having in mind, let's look at our solution. Okay, so now we have two modes, of course, because we know that this is a coupling of plasmons in of each interfaces. Okay, and there are two ways that this mode can be coupled. So these you can consider these plus as a charge. Okay, charges, plus charges and negative charges, and here are negative charges and plus charges. So let's look at the IMI, insulator metal insulator waveguide first. So here plus charges and negative charges and plus charges. So they are old mode. okay, because their charge distribution is odd function as a function of z, okay, and this is even mode because they have plus charges here and minus charges there, and plus and minus, and so on. Okay, so okay, so this is a spoiler, but anyway, yeah, what I was gonna ask was which mode would have a higher frequency at the same beta, at the same wave number. Can you guess like which one has higher frequency? Yeah, old mode, because it, and the answer is yeah, this is pretty right. So Chanung gave a right answer. So old mode here, of course, correspond to the breathing mode in the two pendulum case, right? They are out of phase. And then even mode, they are in phase, so that they have a lower energy. But more fundamentally, if you look at this charge distribution, it becomes obvious, because if you look at the charge here, so this charge plus charge feels restoring force from these guys, right? And also from these guys, right? And now if you look at these charges, feels the restoring force from this one and that one, okay? So the net restoring force that this plus charge feels is stronger in this case, right? Because these charges are closer than these two charges. So I mean, basically this one is basically the same, but this one is closer than that, okay? So if you calculate the net restoring force, this one has stronger restoring force. Stronger restoring force means high K vector, high spring constant, which means high energy, high frequency, right? And and let's also ask you another question about the opposite case. So let's say, let's imagine you have M here, and I here, and M here. Similarly, MIM waveguide instead of IMI waveguide. Then now you have charges at this interface, not here, right? And so charge distribution looks like that. So in this case, which one do you think have higher frequency? Any guess? It's not easy, right? The reason why this is not easy is because in this case, the original case, things are obvious because they feel the restoring force here and there, and then charges can freely move inside the metal, right? So the way they feel the force and the way they can move are kind of easy to interpret. But in this case, when it becomes MIM wave, then now, even though these charges feels force due to these charges, this charge cannot move in this direction, right? Because here's the insulator. So charges can only move like around here, and these charges are only move around here. they cannot have a diagonal motion. And because of this, the situation is actually complicated. So the answer is it depends. Sometimes old mode has higher frequency, sometimes even mode have higher frequency. So it becomes a bit complicated in this case. But in IMI case, it's easy enough, simple enough. So old mode has always have even mode. And another thing I want to say about old mode and even mode is that when you say old mode or even mode, you should be very careful about which quantity is odd or even in this field. So for instance, odd mode, what I mean by odd is charge distribution is odd, okay? But if you draw the magnetic field distribution, it's even in this case. And similarly here, the charge distribution is even here, but the magnetic field is odd, okay? So when you say even mode and odd mode, you better be clarify which field or which quantity you are talking about. Here, what I'm talking about is charge, okay, charge distribution. Okay, so any questions so far? Okay, you can ask question again anytime, any point of time as you want. So wave solutions are, again, the mathematical framework is exactly the same. What you do is along the propagation direction, here it's set as x, along the propagation direction, it has e to the I beta x dependence. So it's like oscillating. And again, beta is kx, which is a propagation constant. Okay, you can be confused because sometimes I set z as propagation direction and sometimes I set x as propagation direction. That's entirely depending on how our textbook is defined. But anyway, here it's defined in x direction. Okay, and then I decays along z direction, so exponential decay, which is the we have basically guided mode. And so electric field and magnetic field are both exponentially decaying with this dependence. Okay, so before I move on, Hui asks, what's the difference between PEC waveguide and plasmonic waveguide? Do they use the same principle? This is really good question. Really, really good question. So of course, PEC waveguides and plasmonic waveguide share some property, but the biggest difference is that PEC waveguide assumes the conductivity of metal to be infinity. Okay, and because this is infinity, epsilon is also infinity. Okay, epsilon is actually negative infinity, but anyway, epsilon is also infinity. Okay, and here what we're solving in plasmonic case, epsilon is negative, but finite. It's not infinity. Okay, and that makes a few differences in actual solutions. The representative example is IMI waveguide. So think about the case that you have a PEC core and epsilon d here. This is not even a waveguide, right? Because no wave can exist in the PEC. So there's no, there's no guiding solution basically in this case, in this PEC IMI waveguide. But in this case, in actual metal with finite epsilon, now you have field inside the metal is allowed, right? So that you can have a solution in this case. So the biggest difference between PEC waveguide and plasmonic waveguide is basically the assumption on the metallic material. In PEC, the conductivity is infinity, so epsilon is also infinity, but plasmonic waveguide, it's not. They are all finite, but negative. Okay, so now, if you set this way, set in this way, then the allowed solution, and what we know about the plasmon is that at the interface, the field are exponentially decaying in both directions. So field outside the metal exponentially decays, but field inside the metal also exponentially decays, right? So if you have an exponentially decaying wave, let's say e to the kappa z or e to the plus kappa z, there are two possible combinations. One is cosine hyperbolic. Okay, this is even combination of exponential functions. And then another is sine hyperbolic, which is an odd combination of hyperbolic function, right? So this is basically the ansatz, or the solution form of the inside of metal. And then outside, it's exactly what I wrote here. So e to the I beta x in the propagation direction, e to the minus gamma z in the surface perpendicular direction. So this is the solution form, right? And then from wave equations, we know that kx squared plus ky squared plus kz squared is epsilon omega over c squared, which is epsilon k0 squared. Okay, so this is true for all wave, right? All wave, any wave should satisfy this condition. And we know that along y direction, there's no variation, so we can ignore this. Along x direction, the wave propagates. So kx is beta, right? So this becomes beta squared. And then along z direction, kz is basically I gamma, right? So that you have exponentially decaying wave in kz direction, right? Outside in the epsilon d regime. So in epsilon d regime, in the cladding, you have beta squared minus gamma squared is equal to epsilon d k0 squared. This equation becomes like that. And then inside the metal, similarly, beta squared minus kappa squared is equal to epsilon m k0 squared. Right? Here kappa is this kappa here. Right? So what I'm doing right now is basically same as what we've done for dielectric waveguide. The only difference here is that we assume not the trigonometric function, but we have cosine hyperbolic and sine hyperbolic functions inside the metallic regime. Okay. Okay, so now we have all ingredient. Okay. So for what we need to do now is applying boundary conditions. So from the boundary conditions, say electric field and magnetic field are continuous at the boundary. And for odd mode, you get these two conditions. So don't worry if you cannot follow this real time, because it's impossible. You are just, all you need to do is to check that you are following the logic here. So for even mode, if you apply the boundary conditions for H and E field, you get this equation. Okay, and these two equations can be simplified to this for odd mode, and these two equations can be simplified to this for even mode. Okay, so look at this. It's like the only difference between these two is that this one is tangent hyperbolic and this one has cotangent hyperbolic. And of course, that's the only difference, right? Because odd mode, you have cosine hyperbolic. Even mode, you have sine hyperbolic. So it's like how it's organized. And then we normalize this so into the gamma, normalize gamma by using K0, and normalize kappa again by using K0. We can make equation simple, and then using these two equations and another equation in the previous slide. So previous slide, you have the final equation here. This equation here. So you and then you try to solve the equation by, again, graphical manner. So that's this. So here, what I drew is blue is even mode, for even mode, and then red is for odd mode, and then why many lines? Because we have many different A. A means the thickness of the metal. Okay, so this solid line is thinner metal, and the dotted line is thicker metal, and then this black line is infinitely thick metal. Okay, this black straight line, this black dotted line is infinitely thick metal. And then here the red thing the same, but it's odd mode. And then here blue, black solid curve is the equation from the wave equation. So what we need to check is the crossing of these two curves, and that gives you the answer. Okay, so what do we know? First of all, at the same omega and thickness, if you compare the overlaps, the even mode and odd mode, okay, the same thickness, even mode has higher gamma and kappa compared to odd mode. Okay, large gamma and kappa. Large gamma and kappa means it's more tightly confined, right? Remember, gamma and kappa is used for e to the I gamma z here. So when gamma is large, that means it's tightly confined to the interface. So even mode is more tightly confined, and odd mode is less tightly confined. Okay, so that's one big difference. And then you can compare this also with A here. So A goes to infinity. When A goes to infinity, then here, this is the infinitely thick layer case, which is same as single interface. Single interface. So compared to single interface, even mode is more confined, odd mode is less confined. Okay, and as A decreases, so as the thickness gets thinner and thinner, even mode becomes more and more confined, odd mode becomes less and less confined. Okay, so that's what you can extract from these graphical solutions. Okay, so this, I guess this is easy enough. Okay, so now let's look at the actual dispersion relation. So this is your dispersion relation of IMI waveguide. So if you look at this, here's the even mode and here's the odd mode. So again, at the same frequency, this is single interface plasmon, and this is odd mode, and this is even mode. You can see that even mode is much more confined compared to single interface or odd mode, right? You can immediately notice that. And then, yeah. So again, that's for the same frequency. And then for the same beta, odd mode has higher energy compared to even mode, as we discussed before. Again, odd mode is about discharge distribution, and even mode is discharge distribution. So odd mode has higher energy, as we expected. And another interesting point is that odd mode can have negative group velocity, right? This is another interesting point. So you can see here the slope of the dispersion of the odd mode is negative, which means odd mode has negative group velocity. So that you can, by using this property, you can basically create a negative index material, negative refractive index metamaterial, which I will explain later in the metamaterial lecture. Okay, so here is how the actual IMI waveguide works. So here you can ignore this this curve above, but so this is like SiO2 silver SiO2 waveguide, and then here we draw even mode and odd mode. Again, even mode has longer k vector or lower frequency compared to the plain the single interface plasmon. You can ignore the upper part. And here, the odd mode has higher frequency or shorter wavelength, shorter beta compared to the single interface plasmas. So this is lossless case, okay? Assuming that there's no actual loss in the system. And in real material, if you put actual material properties of silver and SiO2, now you have finite this behavior that you saw in your a single interface plasmon case, and you can see it has the even mode has very large k vector, while odd mode has relatively small k vector, okay, compared to even mode. And then if you look at the field penetration into silicon dioxide, which means field penetration into the silicon dioxide means you have like metal here, silicon dioxide there, and then you have this field penetration, which is e to the minus gamma z, and the field penetration is this portion, okay, which we call this as a skin depth. Okay, for the even mode, as the thickness of the metal gets smaller and smaller, the skin depth also gets smaller, which means if you make the device thinner, confinement goes up, okay? And for even mode, for odd mode, it's exactly the opposite. So if you make the device thinner, then the confinement actually becomes more loose compared to the single interface, okay? And if you look at the propagation distance, how long it can propagate without loss, for even mode, you can see that when the thickness becomes thin, propagation distance significantly reduces, okay? So here we can again see the trade-off between propagation and confinement. So as the thickness becomes smaller, it becomes more confined, but more lossy at the same time. So it's always like satisfies this kind of trade-off relation. And in this case, in the opposite case, when you make things more confined, when you make the core thinner, it becomes more loosely confined, and at the same time, propagation length also increases. Okay, so propagation length also increases in this case. So how come this is possible? It's, you know, when I just mentioned this, it's probably not that intuitive. But if you draw the charge profile, it's actually pretty. It becomes pretty obvious. But probably probably for the sake of time, I'm not gonna draw this at the moment. But let me introduce one paper to you guys. So from now on, what I'm going to cover is this paper, written by Jennifer Dion in 2005 on Physical Review B. Okay, and typically the papers on Physical Review B is not cited that much, but if you look at this paper, yeah, so I'm talking about this paper, and this paper is cited by 1,200 times, which is a lot, right? And then if you look at this paper is written by Jennifer Dion, and then now she's a professor at Stanford University. And then you can actually see this looks like pretty much like a kind of textbook, Plasmonics textbook. So you can begin with the electric field and magnetic field profile form, and then begin with this ansatz that exactly I did, like tangent hyperbolic, cotangent hyperbolic functions. And then here again the momentum conservation condition, the wave equation. And then you find two solutions. And from here, it's basically just covering all different cases of MIM waveguide, IMI waveguide, and their properties. Here you see the propagation distance, and also how the field's distributed. So this is very, very, how can I say, well organized. It's not about anything profoundly new, but this paper organizes how to kind of derive things, and then the properties of a plasmonic waveguide in a nice one paper, and it got cited by a lot, like 12,000 times. I'm sorry, 1,200 times. So this is another way of having a high impact paper, actually. You find a important contemporary topic, and then create a comprehensible review of the topic, and it will get cited by a lot. Okay, so if you are very interested about this thing, I recommend you to basically read the paper, okay, thoroughly. And my presentations, this lecture notes, is actually based on that paper, this paper. Okay, so one big difference between dielectric versus metallic waveguides. So if you recall the dielectric waveguide, the guiding mechanism was total internal reflection, right? Total internal reflection. And then when the thickness of the waveguide is much larger than when the thickness of the waveguide is much larger than the wavelength. What happens is that you have very small field penetration here, right? And the let's say lateral size of the mode. So here it's specified by the dashed line. Okay, lateral size of the mode is very similar to the actual thickness of the waveguide. Okay, and now imagine you make this waveguide thinner and thinner. Okay, at some point, what happens is that the field penetration into the cladding becomes larger and larger, and eventually this becomes like a plane wave, as we solved in our midterm exam, right? So in this case, the size of the mode, let's say you set the size of the mode like, let's say this is the amplitude 1 and this is 1 over E, then the size of the mode is actually larger than this case. Okay, so you basically have a minimum mode size that you can achieve with dielectric waveguide. And that minimum mode size is similar to lambda, the wavelength of the light. Okay, and this is called, again, diffraction limit. Okay, so you cannot compress the light below certain bound, which is diffraction limit. Okay, so this is typical dielectric waveguide. But metallic waveguide, the situation is completely different. Okay, so metallic waveguide, as we saw before, the field penetration and the beta always goes together for even mode only. Okay, so if you make the waveguide smaller and smaller, I mean thinner and thinner, you basically make your field penetration smaller and smaller, and so if you make this infinitely thin, you can make your waveguide, I mean the size of your guided mode, to be very small, compressed a lot, much below the diffraction limit. Okay, so this possibility makes people very excited about like 10 years ago. Okay, when this possibility has first spotlighted. Okay, so this is very fundamentally different. Dielectric waveguide, no matter how thin the waveguide is, the actual mode size is limited by lambda, diffraction limit. But metallic waveguide, if you make waveguide very thin, then you can make your mode actually be very thin, far below the diffraction limit. Okay, and yeah, so I don't want to cover too many things today. So this will be my final slide in today's lecture, for today's lecture. So far, what I have covered was IMI waveguide, insulator, metal insulator waveguide. And now I want to move on to metal insulator, metal waveguide. Okay, so metal insulator, metal waveguide is very interesting because you probably remember when you solve the midterm exam, we actually had similar problem of PEC, and insulator, right? Do you remember what was the fundamental mode of a fundamental TM mode? So the fundamental TM mode in was actually look like look like this. Okay, so this was the fundamental TM mode, and then TM mode begins like this, and then second order, third order, and so on. And here, the difference is that now this metal permittivity is not infinity, so you have field penetration allowed inside the metal. Okay, PEC waveguide, this was not allowed. Okay, and so basically the metal insulator metal waveguide behaves similarly to the PEC waveguide when the thickness of dielectric is large. When the thickness of dielectric is large enough, then this basically acts as a, I mean, it supports like many modes, like a fundamental mode. I mean, this is fundamental mode, and the second order mode, the third order mode, fourth, and so on, as we learned in the PEC waveguide, right? So behavior is pretty similar, but it becomes different from the PEC waveguide when the insulator becomes thin, so that this field penetration becomes more important. How you solve this? The solution, the way you solve this is actually the same. So you need to do similar to the previous case. You first satisfy the wave equation, and also you set the ansatz of the mode, okay, the odd mode and even mode, and then apply the boundary condition and solve it. The process is exactly the same. So from next lecture, I'm going to explain in detail how the solutions of the MIM waveguide looks like and why this is the case, and then move on to some of the applications. So okay, so this is pretty much, this is a lot. So yeah, so in next lecture, I'll begin with this metal insulator metal waveguide, and then I'll go on from here. Okay, so any question in today's lecture? I guess this lecture and the next lecture might be a little tedious, because it's all about derivations. So I try to convey the key idea as interesting as possible, but still it would be a little bit tedious. So I just decided to make one lecture a little bit shorter to help you maintain the concentration. Any question? Okay, if not, I will stop here.